Oh, yeah, I know. You were all looking at that. Is he going to press record? It's almost like we're playing Uno, right? You ever play Uno, and if you set down your second to last card and you forget to say Uno and somebody says it before you, then yeah, it'll be a contest. Well, we have started in on glycolysis. We talked about an overview. In the end, we're taking a 6-carbon carbohydrate. We're converting it into two 3-carbon molecules of pyruvate. Along the way, we're making 2 ATPs and 2 NADHs. And then those 2 molecules of pyruvate go into this dehydrogenase complex. We lose 2 molecules of CO2, and we end up with 2 molecules of acetyl-CoA. So we've lost 2 of our 6 carbons of glucose as CO2. We make another 2 molecules of NADH. And with the idea that in the electron transport chain in mitochondria, we can convert each molecule of NADH into 2.5 molecules of ATP, we calculated that up through glycolysis and the dehydrogenase complex, we get 12 molecules of ATP, and that's what we use to live and breathe and think and move and everything. So we started in, and the first step of glycolysis was to phosphorylate the C6 hydroxyl group. We do that with ATP. We talked about how that converts a level 1 electrophile, a phosphoanhydride, into a level 2 phosphoester, and so that's downhill. We talked about how enzymes that catalyze phosphate transfers are called kinases. We talked about how this reaction, being so downhill, is irreversible, meaning a molecule of glucose that gets phosphorylated is totally committed to glycolysis. And then we skipped ahead and we talked about the conversion of fructose 6-phosphate into fructose 1,6-bisphosphate, where it's now the C1 hydroxyl that becomes a phosphoester by transfer of the gamma phosphate from ATP to ADP, again by a kinase, and you end up with this molecule fructose 1,6-bisphosphate. The bis means two phosphates, and you have a phosphoester on the C1 oxygen and on the C6 oxygen. So on both extremes of the molecule, you've got a phosphoester. We anticipated that this reaction would be irreversible as well, very downhill, because again, you're taking a level 1 electrophile phosphoanhydride in ATP and converting it into a level 2 compound, the phosphoester. So those are the 2 kinase steps. We even drew the mechanism for that. And as you recall, we're doing this always through an addition-elimination mechanism. So we talked about how a base will remove the proton from the C6 hydroxyl of glucose, that nucleophile will then attack the phosphorus, and then we'll break the phosphorus oxygen pi bond, get to an intermediate which has 5 things attached to phosphorus. Electrons kick down and eliminate the leaving group, which is ADP. A good leaving group because it's the conjugate base of a decent acid. And then after that elimination, we have the phosphoester. Okay? Some of you have asked, why doesn't this happen by direct substitution? That is, why doesn't the nucleophile attack and the leaving group leaves? And the answer to that has to do with HOMO and LUMO. We're just going to consider real briefly how reactions happen with carbonyls. Here is let's just do a thioester. And let's do a reaction in which an alcohol replaces a thioester to give us an ester. This is a level 1 electrophile. Esters are level 2, so this is downhill. And it looks, and it is, a substitution reaction overall in the sense that the SR leaving group gets replaced by the OR nucleophile. Nevertheless, the mechanism here is not as follows. The mechanism here is not that the base removes a proton and then this happens. Instead, the mechanism involves, I need to move the knot up here. The mechanism involves first base removes the proton, then we attack the carbonyl carbon, and then we get a tetrahedral intermediate where the carbonyl carbon is attached to four things, and then electrons kick down and the leaving group leaves. The overall effect of the addition and then elimination step is a substitution product where the leaving group has been replaced by the nucleophile. But my question to you is, what's the difference between these two mechanisms? Some of you are saying, well, they lead to the same thing, so what's the big deal? Let me ask you this. In the way the mechanism actually is, what is the LUMO on the thioester? The pi star, the antibonding orbital between carbon and oxygen's pi bond. That's the lowest energy orbital. That's the place where the nucleophile has to attack. If you are doing direct substitution, what orbital are you saying is getting attacked instead? Right, direct substitution, and this is something to remember. Direct substitution requires attack on the sigma star between the carbon and the leaving group. And the problem here is that's not the LUMO. So you want to know why it doesn't happen by direct substitution? Because here, that is not the LUMO. Here is the, if we had an energy, and here were all the filled bonding orbitals, and up top were the anti-bonding orbitals. The pi star is here, the sigma star is here. The nucleophile is going to attack the lowest energy orbital, the pi star. Go ahead.
So for direct substitution, it's always just going to attack the sigma star.
That's right. Direct substitution is always attack of a sigma star. So when does direct substitution happen? Well, you need a molecule where you have a low energy sigma star and no pi star. For example, consider this alkyl halide. There is no pi bond. The weak bond is the carbon chloride bond. So the LUMO is the carbon chloride sigma star. Because that's the LUMO, it's totally reasonable to do the direct substitution mechanism, which gets you a new bond between the nucleophile here and the carbon that used to have the leaving group there. So you do see direct substitution in chemistry, but only when the LUMO is a sigma star. Okay, does that clear things up a little bit? So we're gonna, for phosphoanhydrides, phosphoryl and carbonyl compounds, we're always gonna consider the LUMO. For these level 1 electrophiles, we're always gonna consider the LUMO to be the pi star. And that's why you attack and you break a pi bond and get the intermediate. Go ahead.
So if there's a pi bond present, it can't be direct substitution.
If the carbon that has the leaving group is also doubly bonded to an oxygen, then it's not going to be direct substitution. Yep. Okay, other thoughts? Okay, well, let's see. I think actually I needed to start a new set of notes. So let me just copy that, and we'll paste that in there, and then we'll be good to go. All right, what I asked you to do to prepare for today was to look at this reaction called an isomerase reaction, glucose 6-phosphate isomerase, where we're going to go from glucose 6-phosphate to fructose 6-phosphate. I told you to convince yourself that the open chain form of glucose 6-phosphate was an aldehyde, and then to convince yourself that the open chain form of fructose 6-phosphate was a ketone. I also wanted you to push arrows to show me how glucose 6-phosphate becomes the open chain form. So we don't have a lot of room here to do that. Let's just skip down, and you can, based on what you did, sort of talk me through it. So here is the anomeric carbon. I'm using straight lines to indicate I don't know or care whether they're dashes or wedges. Let's see. For glucose, it's down, up, down, and then up, except I need more space. So that's glucose 6-phosphate. It may help you to number the carbons, and on the carbonyl carbon, or on the anomeric carbon rather, it may help you to identify the OH group versus the OR group. It may also help you to identify the two non-oxygen things attached to the anomeric carbon, the hydrogen in that case, and then the C2 group. All right, so what's the open chain form going to look like? What should carbon 1 be? Okay, carbon 1's got to be a carbonyl. So I can draw it in basically the same way. I just need this and then the hydrogen. Notice the gray hydrogen and gray C2 stay exactly the way they are. Notice that what used to be the OH group and the hemiacetal is now the carbonyl oxygen. Notice that what used to be the anomeric carbon is now the carbonyl carbon, and then everything else in the molecule, most everything else, is exactly as it was. Here's the C5 hydroxy, well, here's the C6 phosphoester. How about the C5 group? What should the green oxygen be now? Going to be an alcohol having left, all right? So this is the cyclic hemiacetal form of glucose. This is the open chain or linear form of glucose. Questions about how I did that? Is that the answer you came up with? Go ahead.
Is there a reason you said hydrogen missing on the phosphoryl group, or is it just?
Oh, that was just me being in a hurry. Both forms, the monoanion and the dianion, are reasonable at pH 7.2 or 4, whatever it is. Okay. Yeah.
Do we have to talk about hydrogen where is that?
The hydrogen where?
The gray hydrogen?
This one? No, for the aldehyde, it would be correct and fine just to draw it like this. The hydrogen can totally be implied in skeletal structures. I added it here just to make it absolutely obvious that this was an aldehyde and to make sure that you knew that nothing disappeared. Yeah, go ahead.
How did the oxygen gain that hydrogen?
Yeah, how did this OH gain the hydrogen? And you could also ask, how did this one lose it?
Yeah.
Yep. So we'll explain that in the mechanism. You're going to need proton transfer reactions to make that happen. Was that another question too? I saw another hand. Yeah.
I was just wondering if you were going to go through the mechanism.
Yep. Yep, that's next. So you've already seen, and this is, if you're not sure what to do, comparing before and after is a really great way to get an idea, because you've noticed this group doesn't have a hydrogen, but now it does. So that's a clue you got to do a protonation reaction. This group has a hydrogen, now it doesn't. That's another clue you need to do a deprotonation reaction. So what the mechanism would be, and I hope you tried this and compare your answer to what I'm about to show you. You need some basic group, possibly from the enzyme, possibly water. The open chain form is in equilibrium with the hemiacetal. You remove this proton, then the negatively charged oxygen kicks down and kicks off the leaving group. That's what creates the new pi bond. Then, as the leaving group is leaving, it's going to pick up a proton from some acidic group, possibly an enzyme side chain, possibly a water molecule. So that's all you need to do for chain opening. This arrow, if we're being sort of specific about what these arrows represent, this arrow represents deprotonation, an acid-base step. These two arrows represent elimination. Lone pairs adjacent to a leaving group kick down to make a pi bond and leaving group leaves. And then this sort of represents a protonation step. And we're going to be okay condensing proton transfer steps with either addition or elimination steps, mostly just to save time. If you wanted to draw it out stepwise, where you do the deprotonation first to get a negatively charged pink oxygen, then you do the elimination step, then in the next step you protonate the green negatively charged oxygen, that's fine too. We're just doing it all at once to save a little bit of time. All right, other questions about that? That's a hemiacetal hydrolysis reaction, is another way to talk about it. Now, let's do fructose over here. So this will be the cyclic hemiacetal form of fructose 1,6-bisphosphate. Let's make sure, fructose, yeah, just fructose 6-phosphate. Trying to make sure I get the structure right. This is the C1 hydroxyl group, the C2 hemiacetal oxygen. And then the rest of the stereocenters in fructose are actually the same as they are in glucose. That is, for fructose on C3, you have an up OH, C4 a down OH, C5, you have an up carbon 6 with the phosphoester on it. Now, again, following the same pattern, identify the hemiacetal carbon, the one that's bonded to two oxygens, find the OR group and the OH group, then find the other two non-oxygen things. In this case, both of them are carbons. So that's a clue that the open chain form is going to be a ketone. Let's draw the open chain form of fructose, and you can tell me what you found. So the C5 oxygen should be what? What should this group end up being? Good, because that's the leaving group. The C6 phosphoester is going to be exactly the same. C4 and C3 are not involved. How about C2? What should be the key functional group on C2 now? Yeah, gotta be a doubly bonded oxygen. That oxygen is the pink hemiacetal oxygen, and carbon 2, which is the ketone carbon, used to be the hemiacetal carbon, and then over here we have C, the C1 hydroxyl. I'll label these green, or sorry, these are gray. This was our green leaving group. Now, as we do this mechanism, I told you not to worry about drawing the ring opening mechanism here, in part because you've already drawn it here and it would be the same thing, but second, because the reaction in thinking about glycolysis proceeds from glucose 6-phosphate to fructose 6-phosphate, so the forward direction is towards the cyclic hemiacetal of fructose. In other words, at the end, we're actually going to show the ring closing mechanism. Any questions about this open chain structure? All right. Here's the fun part. How do they interchange? We need to connect the dots. Connecting the dots requires you to remember something that I think you've learned on a problem set and then probably forgotten. So we're going to zoom in here on the open chain form of glucose 6-phosphate. And the observation is this. Protons that are alpha, meaning adjacent to, protons that are adjacent to carbonyls are more acidic than expected for an sp3 hybridized carbon-hydrogen bond. Do you remember the reason for that? Why being alpha to a carbonyl might make you more acidic? Any ideas? Go ahead.
Is it because of resonance?
Yeah. If you remove a proton that's adjacent to, and I'm just going to simplify the structure, if you remove a proton that's adjacent to a carbonyl, sorry, I guess we're going to need an OH group there. Notice that that negative charge is stabilized by resonance. It's not held exclusively on the alpha carbon, but is also delocalized through resonance on the oxygen. In other words, if you would conclude that that negative charge on the alpha carbon is in both places at once. It's simultaneously on the oxygen and the alpha carbon, because that's what resonance means. Okay? A conjugate base that's stabilized by resonance means that the corresponding acid is more acidic than expected. Okay? This is an important feature. You've learned it on problem sets. You're going to need to keep it in mind for metabolism. Protons that are alpha to carbonyls are somewhat acidic. Okay? So with that in mind, I'm gonna, and once you remove the proton at this alpha carbon, you have a choice. You can put the proton back on at the alpha carbon or on the carbonyl oxygen. So I'm gonna ask, what would happen if we protonated this oxygen? What would the product be? You're gonna have an alcohol there, right? This intermediate is called an enol. And you saw keto-enol tautomerizations last week on our mechanism handout, and you can go look that up again to see how it happens. Keto-enol tautomerization refers to the fact, if this is the keto form of a carbonyl, this is the enol form of a carbonyl. And those two are in equilibrium with each other, though the keto form dominates. And the intermediate in this pathway is the so-called enolate, this resonance stabilized molecule in which the negative charge is delocalized on both the alpha carbon and the carbonyl oxygen. Okay? Is that sounding familiar? Ketone, enol, enolate is the negatively charged thing. So ketones and enols can interchange. The process is called tautomerization because a tautomer is an isomer that varies in the location of a pi bond and a proton. So if you compare the keto form with the enol form, recall that the proton changes from being on the alpha carbon to being on the oxygen, and then the pi bond changes from being between carbon and oxygen to being between two carbons. Okay? That's important background for what we're going to do next. Questions about that foundation? All right, good. If you think of any, we can circle back to it. So, what we're going to do now. Normally, when you show tautomerization, it's traditional to show the proton transfer to make the enolate first in one step. So that would be, if you imagine that would be base removes this proton, and we put the lone pair on the alpha carbon. Then these two are resonant structures of each other, and if you wanted to show interchange of those resonant structures, you could simply do this, push to form a pi bond, put the lone pairs out on the oxygen. So you draw the enolate intermediate, and then you would show it getting protonated on the carbonyl oxygen, and that would give you the enol. You are still free to do that stepwise, the way I've shown it here. But because they're proton transfer steps, I'll show you a equivalent way that you can draw this. That would be to have some base side chain, remove the proton from the alpha carbon, have electrons kick down to form a pi bond between the alpha carbon and the carbonyl carbon. Then show the electrons, instead of showing the electrons coming up and being on the oxygen, understand that the carbon-oxygen pi bond is going to break, the oxygen is going to become negatively charged. Let's have it actually pick up a proton from some acidic group in the enzyme side chain. And let's do that all in the same step. All right, so this combines the proton transfer to make the enolate with the proton transfer to make the enol from the enolate. You see what we're doing? Any questions? All right. Let's draw what that structure is. And we'll just remind ourselves with equilibrium arrows that this reaction is totally reversible. We're going to draw it in the forward direction, but it could proceed in the reverse direction. Here's the C5 hydroxyl, the C6 phosphoester. Give myself a little bit of room. Move those arrows over just a little bit. C4, C3, C2, and C1. So 1, 2, 3, 4, 5, and 6. Stereochemistry at 4 and 3 stay the same. Now, because of enol formation, there should be a pi bond between 2 and 1. 2 is still attached to an OH group, but now 1 is as well. Okay, so just to keep things straight, this used to be our carbonyl carbon. This used to be our carbonyl oxygen. The proton that is here on this OH group used to be attached to C2. So conceptually anyway, whether it's exactly the same proton or not, doesn't matter. Okay? The electrons in this carbon-hydrogen bond are now here in this pi bond, and we now have a hydrogen. This is the tautomerization. We moved the hydrogen and the pi bond. Okay, I guess I don't necessarily need that highlighting. All right, Questions about that structure? Now, go ahead. No?
So, sorry, just so I can get it straight. So it was the base that attached. So how does the double bond go from the carbon 1 to carbon 2?
So we get the double bond between 1 and 2 by removing the alpha proton. Then these electrons in the bond between carbon and hydrogen kick down to form a pi bond between 1 and 2, and then we break the carbon-oxygen pi bond, which puts all in one step what I showed you here. Base removes the proton to put the lone pair on the alpha carbon, then the electrons on the alpha carbon by resonance go on to the carbon, make a carbon-carbon pi bond with a negatively charged oxygen. Then we protonate on that negatively charged oxygen to get the enol. Yeah. Good. Other questions? Yeah.
Could it possibly go between the electrons after the hydrogen is deprotonated? Like, could that 2 carbon, could the electrons go between 2 and 3, or that's just not what?
Right. Could the electrons, conceptually you're saying, if I remove the proton, could the electrons kick down here to form a pi bond between 2 and 3? No, because there's no leaving group or pi bond to break on carbon 3.
Yeah.
Yeah.
And the hydrogen doesn't have anywhere to go.
And if you tried to kick off a hydrogen, it would have nowhere to go. Yep, good. All right, now this intermediate, our enol, is actually a unique and special enol. It's called an enediol, okay? And here's the tricky thing. Prior to forming the enediol, C1 in blue had been the carbonyl carbon, right? It had been the aldehyde. And and the pink oxygen had been the carbonyl oxygen. But notice that this enediol is an enol in both directions, okay? So here is the blue carbonyl carbon, and here is the blue alpha carbon. But over here on C2, what if I say, let's have C2 be the carbonyl carbon, and this be the carbonyl oxygen, and then let's have C1 be the alpha carbon. Do you see how that enediol is an enol in 2 directions? Tautomerization got us to that enediol from a molecule that had the aldehyde on C1 and a proton and an OH on C2. Through a similar tautomerization step, we can convert that enediol into fructose. Normally, so let me show you actually how before I show you conversion to fructose, let me show you how an enol goes back to the carbonyl compound. Okay? To do this, a base would deprotonate the pink OH group. Electrons would kick down to reform the carbon-oxygen pi bond, and the carbon-carbon pi bond would break, and a hydrogen would be added to C2. And that would take us right back to glucose. That's how you tautomerize from an enol back to the keto form. Go ahead.
Okay, I'm just trying to put this in words that I can understand better. So like tautomerization is like an Uno reverse between like carbon 1 and 2. Like now that was the alpha carbon, the other was the carbon.
So tautomerization, I think you're jumping a little bit ahead. You're right that, today is the Uno analogy. What we're about to do with the enediol is play Uno reverse with tautomerization. Now go in the other direction. What tautomerization means, though, is it's 2 proton transfer reactions. You remove a proton from one place, get a resonance stabilized intermediate, and then add the proton on a different atom. In so doing, you move the location of the proton and the location of a pi bond. So the enol is a tautomer of the aldehyde. Now, to go back, if I wanted to go back to the aldehyde, that would be as simple as deprotonating the pink oxygen, electrons kick down, and then I reprotonate on the alpha carbon. That's the exact backward step that gets me this way, right? Now let's imagine that I told you the ene diol is a special intermediate. I need to use different colors. Let's use orange for this OH group. And let's use, I don't know what to use. Green we don't want to do. Red is too close to pink. Purple, can you tell the difference between pink and, that's kind of green. We'll use green, all right? So before, the blue carbon was our aldehyde carbonyl carbon, and carbon 2 was alpha to the aldehyde. But you can see this ene diol has another potential direction. In green is another potential carbonyl carbon, and now the blue carbon is alpha to that. So I can do a separate tautomerization reaction where I deprotonate the orange carbon, orange oxygen. Electrons kick here, then here to restore the pi bond. Then I break the carbon-carbon pi bond and I protonate on C1. What does that do? Now I need to change the colors I used for fructose, but if you're following along, this is where the pink oxygen ended up. This is where the aldehyde carbon ended up. My green carbon is now the carbonyl carbon, and my orange oxygen is now the carbonyl oxygen, all by proton transfer steps. The idea is that ene diol is a key intermediate that can tautomerize in two directions. It goes to the right, you get back the aldehyde. If it goes, well, right and left are mixed up now. If it goes to the right, you go back to the aldehyde. If you go to the left, you get the ketone. Yeah.
Sorry, now I'm just confused with the colors. It goes after the carbon. Like, our enzyme is going to touch the hydrogen that's touched the carbonyl, or is it to the blue?
Good question. So this bond between C2 and C1, the pi bond breaks. Electrons go on to C1, and then C1 gets protonated by the enzyme.
No, right. I guess, which reaction are you showing right now? Is it
This is the one that goes on to fructose.
right? But which
Sorry, as my mother used to say, you're cutting, used to suggests that she's not still living, which she is. As my mother says, you're cutting and I'm not bleeding, which is kind of a grisly metaphor, but that means keep trying and maybe I'll get it. Go ahead.
Sorry. I just am wondering if this one is the green combination of carbonyl atom and alpha, or is it the blue? Because we thought that it needed a different reaction, and I just can't remember.
Okay, if I deprotonate on the pink oxygen and electrons kick down here and I protonate on C2, that gets me back to the aldehyde. If I instead deprotonate on the orange oxygen, electrons kick down and I reprotonate on C1, that gets me to the ketone. I guess what I was trying to show you is we've chosen a lot of things for labeling that's been kind of confusing. I need more colors. But this used to be in glucose, this was the aldehyde carbon and this was the aldehyde oxygen. In glucose, C2 was just an alcohol and a proton that's alpha to a carbonyl. We've traded that now. Still, I feel like I still haven't answered your question. So you want to try one more time?
So on the EDL,
Yeah.
you said it's special
Right. So the,
Does
go ahead.
the alpha that's used in the reaction determine which reaction is going to happen?
Yes. Does the alpha that gets protonated determine which one? Yes.
Okay, which alpha is the one that becomes the ketone?
Green alpha gets protonated and C2 becomes the ketone.
And that's what gives us
And that's what gives us fructose. Great. Thank you for being patient with me until we got it. Blue alpha gets protonated to go back to the aldehyde.
okay.
Yep. All right. So this can be confusing because you're not sure what to do. That's why you look at the starting materials versus the products. And the key thing to remember for this kind of step is an enediol intermediate. If you can know how to do tautomerization from the starting aldehyde of glucose to get the enediol, and if then once you get to that enediol, you know you need to get to a ketone, then it becomes clear what you must do. Go ahead.
Okay, so if a base attacks the alcohol group on carbon 2, it will become a ketone.
Right.
And if the base attacks the alcohol on carbon 1, it will become an alcohol.
Exactly. If a base removes a proton from the OH on C2, then it becomes the ketone. If a base deprotonates on C1, it becomes an aldehyde. That enediol intermediate can go both ways. In glycolysis, the forward direction is toward fructose. Okay. Now, with that insight, you are prepared to answer a quiz question. Dun, dun, dun. So let me see if I can bring it up. Am I enjoying box? I'm not, just not going to answer that question. All right. Okay, so this quiz question is very, very related to what we just did for glucose and fructose. It occurs at a different step in glycolysis. This is the 5th step of glycolysis. At this stage, we have already broken glucose into 2 pieces. They are 2 3-carbon pieces. You get both of them. One of them is glyceraldehyde 3-phosphate. The other is dihydroxyacetone phosphate. We're going to talk about how that happens in our next segment. But once it does happen, there's an enzyme that actually causes these to interchange. The one that we're going to take forward in the 6th step of glycolysis is this aldehyde. But so far, because of the previous steps of glycolysis, step 4 gives you a 1-to-1 mixture of these 2. You can interchange between the 2 of them using an enzyme called triose phosphate isomerase, and I will give you a hint. This involves an enediol intermediate, which you can get through a tautomerization step, very similar to what I showed you previously. And then once you have that enediol, you can do another tautomerization step to get to the aldehyde. It would have been nicer for me to have arranged these things in exactly the same way. Let me give you a couple of hints. I'm now no longer numbering these according to which carbons they were from glucose. I'm just numbering them so you can see which carbon in dihydroxyacetone phosphate becomes which carbon in glyceraldehyde phosphate. Second, I'm going to use color coding the way I did with fructose and glucose. That is, the carbonyl carbon of the ketone is going to be green. The carbonyl oxygen of the ketone is going to be orange. The carbonyl carbon of the aldehyde is going to be blue. The carbonyl oxygen of the aldehyde is going to be pink. And I'm going to label them on both things. So C2 in glyceraldehyde used to be the ketone in dihydroxyacetone phosphate, and the OH in glyceraldehyde 3-phosphate used to be the ketone oxygen. Similarly, this is the carbonyl, this C1 of dihydroxyacetone phosphate becomes the C1 carbonyl in glyceraldehyde 3-phosphate, and same thing with the pink oxygen, this becomes the carbonyl oxygen, okay? And the key thing to remember is going to be that protons that are alpha to carbonyls are somewhat acidic and can be removed. So I'm going to highlight a proton on C1 and on C2 that are involved in this process. With that in mind, go ahead and use enzyme B, an enzyme-linked base, and an enzyme-linked acid as needed to push arrows through this. Could take you a few minutes. Let's give you maybe 4 or 5 minutes working on it. I'll wander around for questions, and then we'll reconvene. Or I'll just sit up here and eat cookies, maybe. Anybody need a hint getting started? Yeah? Kind of stuff, okay. So, I guess maybe I should have made this clear. I want you to start with dihydroxyacetone phosphate and go to glyceraldehyde. That would have been helpful to know. If you did it backwards, that's fine. That means that's good. So your first step should be, well, part of what you do to begin with should be to remove the proton in dihydroxyacetone phosphate that is adjacent to the carbonyl. Right? You're going to want to do the one that's on the blue carbon. There is one there to the right. That doesn't, and you should remove that proton. That one actually disturbs the carbon. There's some other things you have to do. And in case you want, I'll just show you what we had done previously. in fructose. So what have you done so far? Have you rotated or? Okay. You don't want to start out with rotating the output. Because there's no way to form a high bond between oxygen and that alcohol and carbon. There's no reason to do it. You have to do is remove the
So what's the
No. So in that dihydroxyacetone phosphate, C2 is the ketone. If it's How you doing? Do you need a little bit more time, or are you all ready to talk about it? All right. Let's talk about it. And I'll mention some things that I've seen as I'm walking around. So there's some uncertainty at the beginning about which proton to remove. Oops, no, that's right, that's right. Remember, the pink oxygen is going to become the aldehyde oxygen. The blue carbon is going to become the aldehyde carbon. C2, which is currently the ketone carbonyl, is going to become an OH carbon. And the ketone oxygen is going to become the orange OH group. It's true that in tautomerization, once you get to the ene-diol intermediate, that's the stage at which you start by removing the OH group. But before, if you're either at the ketone or the aldehyde, your first step is always remove a proton adjacent to the carbonyl. Go ahead. Yes, there's a hydrogen that's implied but not shown, and you can fill it in there if you want. Yep. So starting from the ketone or the aldehyde, if you want to do tautomerization, you start by removing the alpha proton. Don't start by trying to deprotonate an OH group. It won't work. It won't get you anywhere. So the first step would be base removes an alpha proton, electrons kick down to form a pi bond. You could, if you wanted to, it would have been totally fine to do that and then draw the negatively charged enolate as an intermediate, and then in a subsequent step show that intermediate getting protonated on the oxygen. Instead, what we have done is say, okay, form the pi bond and protonate form the pi bond between carbons. Then the carbon-oxygen pi bond breaks. It would go out to form a negative charge on the oxygen. Instead of drawing that intermediate, we're going to show the negatively charged oxygen getting protonated directly by some enzyme-linked group. Okay? And if you follow those arrows, they give you, those are the instructions for drawing the ene-diol intermediate, which should look like this. Here's C1, here's C2. I'm just going to use red for the new pi bond that we made. Once you get to that ene-diol intermediate, to get to, and I'm going to abbreviate, can't abbreviate the phosphate group, sorry. Once you get to that ene-diol intermediate, then you're at the stage where going back to the ketone or forward to the aldehyde will rely on removing a proton from the OH group. All right, questions about getting to the ene-diol? Yeah.
Can you do it from the top one?
You can, yeah. To do from the top one, you would simply, you'd remove, sorry, I need red, there it is. Remove this proton, electrons kick down to form a pi bond, then protonate on the pink oxygen. Yep. All right. Other questions about getting to the ene-diol? Yeah.
This is just more for, like, on the test, would you show the additional hydrogen, or would you just, like, we would have to drop it in?
What additional hydrogen?
Like the hydrogen you drew on the carbon one.
Oh, on an exam, I probably don't even draw that hydrogen in for you, at least if I'm going to ask you to draw a mechanism, I assume that you know it's there. Now, in a mechanism question where I'm saying which of these arrows is right, I have to at least draw the hydrogen that's involved. I could have left off the one that's a dash because it's not involved in the reaction, but you would have to know that it was there. That was weird. What just happened there? Oh, now it wants identification. There we go. Yeah. Okay. Others? Yes.
Would we have to show the oxygen, the orange oxygen, linking to the hydrogen, or would that be like 2 steps?
You can do that 2 steps, or you can do it this 1 step. For example, if you prefer to have the electrons go onto the oxygen and show a negatively charged intermediate, that would look something like this. I'm just throwing in R groups willy-nilly, and then in a second step, show protonation like that. That's fine. It's always okay to show proton transfers separately from other steps. I've just included it now I've just done it all at once so we don't have to redraw things as frequently. Okay, so tell me now, if I want to get to the aldehyde, which of the 2 OHs I gotta deprotonate? Yeah, pink/purple, whatever color that is up there. It's pink on my screen. I agree. It's kind of like the blue dress, gold dress thing up there, depending on what you see as pink or purple. All right, so yes, we're going to deprotonate the pink OH using a base. And then electrons are going to kick down to form the new carbon-oxygen pi bond. At the same time, the pi bond between 1 and 2 is going to break. We could show that going on to carbon 2 as a negative charge, and then in a subsequent step show carbon 2 getting protonated. Or we could simply do it this way, where the arrow from the pi bond goes over to this acidic group from the enzyme, and we understand that this proton is going to end up attached at alpha carbon 2, the carbon that is alpha to the blue carbonyl. And that will take you to the glyceraldehyde. Yeah?
So I'm confused why we can deprotonate the alcohol now rather than before. You said it,
Yeah, if you deprotonate the alcohol before you have the ene diol, let me show you what that intermediate would look like. Some of you are trying to get a pi bond out of that alcohol somehow. And the problem with it is you can certainly deprotonate the alcohol. That's not the problem. The problem is once you do it, there is literally no place for the electrons to go. You might be like, why can't I do that? Well, you would need a leaving group or you would need a pi bond on C1 to break, and there's neither.
but could the bond not make a double bond?
Where?
Like it couldn't be a ketone after you take the hydrogen, the electrons become a double bond.
So in order for there to be, I think I saw some of you toying around with the idea of this intermediate. Notice though that in that intermediate, a hydrogen has gone somewhere. Where did it go? And actually, I'm really glad you brought this up, because sometimes we will see enzymes do exactly what is sort of implied by your question, which is, can't I have these electrons kick down and form this pi bond? The answer is yes, but you gotta have something to take the hydrogen. And I'm not talking about a proton, we're talking about the hydrogen with its electrons, leaving as something that looks like H minus. There is a reagent, there is a cofactor that enzymes use as a glove to catch H minus. That's not this reaction, but we'll see something similar to that in the future. Yeah?
So like, when you show us this, it'll always start with like deprotonation. You'll never like move the, like for in that example, you would never move the pi bond, the electrons to come pi bond first and then just kick off the hydrogen. Because you're not kicking off. You start with taking the hydrogen, you don't kick it off.
In reaction, we haven't yet done any reaction that's like this, and I will show you one that's like this really soon. When that happens, you always deprotonate the oxygen, and it's always H- that gets caught, but that's a little bit ahead.
I guess my question is, should we be thinking of it as like hydrogens are taken, not kicked off?
Hydrogens are taken, deprotonated, not kicked off as H- unless you have an oxidizing agent like NAD plus or FAD present. We'll talk about what those are later. Yep. Okay. All right, so hopefully you can see the similarity between this mechanism in step 6 and the mechanism in step 2. Both of them involve moving either an aldehyde to become a ketone or a ketone to become an aldehyde, and both of them involve an enediol intermediate. And notice what both the ketone and the structural pattern that makes this possible. Look at glyceraldehyde 3-phosphate. Here is the carbonyl carbon, and on the alpha carbon there is an OH group. This is an alpha hydroxy carbonyl compound. Alpha hydroxy carbonyl compounds can do this kind of tautomerization via an enediol intermediate. Notice the dihydroxyacetone phosphate. The green carbonyl carbon, this alpha, the carbon adjacent to it, C1, is an alpha carbon. This is also an alpha hydroxy carbonyl compound. And if you go back and look at step 2 of glycolysis, you should convince yourself that both glucose 6-phosphate and fructose 6-phosphate are alpha hydroxy carbonyl compounds. Go ahead.
What makes it an alpha?
What makes it alpha? Alpha is the term we use in organic chemistry for being adjacent to something. So the green carbon is alpha, the alpha carbon there, C1, is alpha to green carbonyl carbon 2. It's next to.
So if it was like, why would it be like carbon 1 that isn't carbon 3?
Carbon 3 is also an alpha carbon. There are often multiple alpha carbons, but it's only carbon 1 that is the alpha hydroxy.
Oh, so you look for one that's like bonded to an alcohol.
An OH group. Yep. That's the structural pattern. Go back and look at our glycolysis, our step 2 of glycolysis, and notice alpha hydroxy there, alpha hydroxy there. That's how you know that they can interchange via an enediol. Well, we have gone way too long, so let's take a minute or 2 or 3 or whatever. Take a break, grab another cookie if you'd like. We'll start up in about 5.